Hi everybody. This lesson is going to be on section 3.3, Cofactor Expansions. Okay. Now, in case you're wondering, we already learned how to find the determinant of a matrix back in section 3.1. However, that involved permutations and it was a very complicated definition, right? So what we're going to learn now is a much better way to do it. So we have to define a few terms first. So definition, let A be an n by n matrix. The minor which we use Mij for the symbol of an element Aij is the determinant of the matrix obtained after deleting the ith row and jth column of A. So in other words, if you have an n by n matrix and you want to know the minor of an element, you delete the row in the column that it's on and you find the determinant of the matrix that you have left after doing that. Okay? All right, so don't worry, we'll do some examples in a moment, but I have to give another definition here. So definition, let's let A be an n by n matrix. The cofactor, which we abbreviate Cij, of the element Aij is as follows. So Cij is just going to be -1 to the power of I plus j times Mij. Okay. So the cofactor is very related to the minor. In fact, they only differ by at most a negative sign. Now, what does -1 to the I plus j mean? Okay, it just means that you add the row and the column that you're talking about and you raise -1 to that power. But an easier way to remember that -1 to the I plus j is as follows. You just follow that pattern, okay? Plus, minus, all the way down for as much as you need, right? For example, -1 to the 1 plus 1 is +1, right? That's why we put a positive right here, because element 1, 1 ends up being a positive. And so an easier way to think about it is just to always create, starting with a plus in the upper left corner, and then just alternate signs in every direction. And that's an easy way to get this guy over here. Okay, that's usually the way I think about it. I don't really think about -1 to the I plus j. This table makes life a little easier. Okay, so that means if you're dealing with you know, one of these guys with a plus sign, the minor and the cofactor are actually identical, okay? But if you're dealing with one where there's a minus sign, then the cofactor and the minor are just a sign apart. Finally, we're going to write down a theorem. And don't worry, we're about to do an example where we calculate all these things, okay? So this theorem, this is called the cofactor expansion theorem. So let's let A, first of all, be an n by n matrix. We can calculate the determinant by expanding on any row or column. So the determinant of A can be found as follows. So you can use row I expansion. So the determinant of A is going to equal, you look along row I and you go from left to right, OI1 CI1 plus AI2 CI2 plus all the way to AIN CIN. Or that's the same as, if we want to use sigma, that's fine, AIK CIK, where k goes from 1 to n. In other words, you multiply all the elements of the matrix with the cofactors of the matrix in that row. So in row I. Notice that the I never changes in here. Or we have column J expansion. The determinant of A is equal to, so now we're going to do the same thing except we're going to fix a column. So A1J C1J plus A2J C2J plus all the way to ANJ CNJ. And that's the same as k equals 1 to n of A, K, J, C, K, J. Okay. So some notes here. Note. We can use this theorem to find the determinant by expanding on any row or column of A. On any row or column of A. So that's why this theorem is so nice, because we can choose any row or column. A good strategy then becomes to pick the row or column with the most zeros. So strategy, pick the row or column with the most zeros. Okay? This is the quickest way to find a determinant. This is the fastest way to find a determinant. It's probably how you did it in Calc 3 when you were looking at the cross product between two vectors. Remember, you created a matrix and you did a determinant, and you probably expanded on a row. So that's exactly what we're doing now. From now on, this is pretty much how we're always going to find a determinant. But I would like for us to do an example, and we're going to be really specific in labeling everything in this example, okay? So let's let A be the following matrix. 2, 0, 4, 1, -1, 2, 5, 8, 3. So we can expand on any row, and so or column, right? So what I'm going to do is I'm going to choose the first row because the first row has a 0 in it, right? So I'm going to write this down here. We're going to do row 1 expansion. Okay. So what does that mean? This means that the determinant of A is going to equal the first element in that row times the cofactor of that element plus the second element in the row times the cofactor for that element plus the third element in that row times the cofactor for that element. Now notice that this guy is 0. 0 times anything is 0. That's why we chose that row, because there's one less thing to calculate. So let's calculate the cofactors one at a time here. Let's start with C11. So we're doing a 3 by 3 matrix here, so I'm going to put this matrix, or I'm going to create my plus minus chart. This is my plus minus chart for a 3 by 3 matrix, but we're actually only going to be using the top row for this, right? Because we're doing a first row expansion, but I wanted to include the whole thing so that you guys see where it comes from, okay? So that means since for C11, because there's a positive there, this is going to be positive 1 times the determinant of what you get when you delete the first row and the first column. We're going to delete the first row and the first column. So I want you to look up here. The idea is if I delete now this row and this column, I'm left with a 2 by 2 matrix, aren't I? So I need to take the determinant of that 2 by 2 matrix. So I'm going to write that down. -1, 8, 2, 3. So what would the determinant of that matrix be? It's going to be -1 times 3 minus 8 times 2. And that gives me -3 minus 16, which is -19. So we get -19 for that. And now we need to find the third cofactor, C13. So what's C13 going to be? We look at our sign chart here. We're still on the positive sign, aren't we? So it's still going to be a positive 1 times. And now I'm going to delete that row and delete its column of the element that we're on. And so we're left with a different 2 by 2 matrix. So I'm going to, let me go back to yellow here. Yes. So I'm going to do 1, -1, 5, 8. And so when I do this determinant, I get 1 times 8 plus 5, right? Because it's going to be 1 times 8 minus 5 times -1, I just get 40. Oh, sorry, no, 13. What am I doing? I was multiplying 8 times 5 in my head. 13, right? So what do we get? All we have to do now is add these two things together. So let's go back to our determinant here, right? Remember our determinant? So I'm now looking at this row right here. Just want to make sure you all understand where I'm getting this from. So this is what I'm looking at now. Remember that? So I end up with 2 times negative 19 plus 4 times 13. That gives me negative 38 plus 52, which is 14. And that's my determinant. And by the way, we didn't calculate the minors here, but what are the minors? The minors are just this piece without considering the sign. But in this case, because the signs were both positive, the minors and the cofactors happen to all be the same. So just as an aside, we didn't need to calculate it separately, but M11 is also negative 19, and M13 is also 13. So notice that you can calculate the minors if you want to, but normally it's not necessary because I just go ahead and do the cofactors right away. Okay. So I'll just leave these off to the side so you guys understand the terminology. Let's do a more difficult example. Let's do a 4x4 matrix. So example. Find the determinant of negative 9, 2, 1, 4, 6, negative 3, negative 5, 0, 2, 1, 8, 9, 0, 0, 2, 1. So as we look at this, we have to think about which row or column we want to expand on. And the first thing I notice is that column 4 has 2 zeros in it, right? So we are going to choose to do column 4 expansion. So this means that the determinant of A is going to equal what? So it's going to be 0 times the cofactor 1, 4 plus 0 times the cofactor 2, 4 plus 2 times the cofactor 3, 4 plus 1 times the cofactor 4, 4. And of course, because we have 2 zeros in there, we're not actually going to have to find that cofactor or that cofactor. So that's going to make our life a lot easier. And let's look at our sign chart here that's going to help us with our cofactor. We have plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. And so we're looking at this column right there. Okay, so those are the signs that are going to be associated with each cofactor. So let's go now with cofactor 3, 4. What is cofactor 3, 4 going to be? So cofactor 3, 4, remember we have to delete the row and the column and then look at the determinant of what's left. Okay, so we're going to delete this guy and this guy. Notice we have to do the determinant of a 3x3 matrix. Yikes. Okay, yes, these can get quite complicated. So we're going to do that here. So let's write down the matrix that we have left after we delete those. We have also, we need to be careful because this is a negative, right? So it's going to be -1 times the determinant of -9, 6, 2, 2, -3, 1, and 4, 0, 9. Remember, we deleted those two things, right? So we can choose, within this guy, we can choose to expand on any row and any column. And let's remember our 3x3 chart. It won't be a bad idea to have this handy because we are going to be dealing with 3x3 matrices also. So yes, this is a reiterative process. I'm going to expand on the third row here, okay? I'm going to expand on the third row, which means it's going to be plus, minus, plus, okay? So let's go ahead and do this kind of all in one shot, okay? So what is this going to give me? So this is going to give me, it's going to be 4 times, remember I have to delete this guy and this guy now, right? And I have a 2x2 matrix there. Okay. And don't forget that I have a -1 in front of this whole thing. So yeah, I should probably not forget that. Let me just write it there so I don't forget. So I have 4 times 6 minus -6. So 6 plus 6, right? And then the 0 doesn't matter. And then I have plus 9 times. And then I'm going to delete this guy and this guy. I'm left with -27 minus 12, right? -27. No, sorry, positive 27 minus 12. Positive 27 minus 12. So that's what I get. So what does that become? This is -1 times 4 times 12 plus 9 times 15, which is -1 times 48 plus 135, which is -183. So that's C34, -183, okay? All of that work just to find C34. So we found C34, now we have to do the same thing to find C44, okay? So what would C44 be? Let's do that on the next page here. C44 is going to equal, let's come back. So we need to look at the last sign here. It's a +1, right? We're looking at the table here. It's a +1. And then we have to delete this and find the determinant of the 3x3 matrix there. Okay, so it's going to look like this. It's going to be +1 times the determinant of the 3x3 matrix that we get. So that would be -9, 6, 2, 2, -3, 1, 1, -5, 8. So that is the determinant we have to find. I can expand on any row or column that I want for this matrix again. So I'm going to go, why not this way? It really doesn't matter which one you choose. So I'm just trying to choose a variety here so you guys see it. And let me remind you that this is the sign table for that column, right? So we know we're going to go positive, negative, positive, okay? So what do we get here? Again, just so I don't keep writing cofactors here, I'm going to, rather than having the sub-symbols and everything, I'm just going to do it in one shot, okay? So we're going to start with negative 9 times, so negative 9 times the determinant of, remember, we're going to delete this guy, and we're left with negative 3 times 8 is negative 24 minus negative 5 times 1. So it's negative 24 plus 5. Negative 24 plus 5. Okay. Now what? Well, now we're here. We need the negative. Negative 1 times 2 times. Now we have to do the determinant of what's left. Determinant, remember, delete that row, that column. So we get 48 plus 10. 48 plus 10. Okay? And now we're on the positives, so it's going to be plus again. And then we get 1 times, delete the row and column it's on, we get 6 plus 6. 6 plus 6. Okay. So what do we get here? We get negative 9 times negative 19 minus 2 times 58 plus 1 times 12, which is 171 minus 116 plus 12, which is 67. So all of that is cofactor for 4, okay? Let me put a circle around what I need, right? I got this guy for cofactor for 4, and I got this guy for cofactor 3, 4. Luckily, those are the only two we had to do because of the 2 zeros that we had, right? So now remember what we're doing here. We're using this formula, and now we need to do 2 times the first plus 1 times the second. So we end up with the determinant of A is equal to 2 times, remember we had negative 183, and then plus 1 times the second, which is 67. This ends up being negative 299. Okay. Now, you can probably imagine determinants are not easy to calculate, right? Now, this is still a much easier method than doing all those permutations and stuff that we learned, right? But in case you're wondering, what about section 3.2? In section 3.2, we learned about all those tricks to make determinants a little bit easier, like using row operations. So let me write this down as a tip. We can use elementary row operations to create more zeros and speed things up a little. Now, you can use this at your discretion, okay? But I just want to show you guys that this is a thing that you can do, because otherwise 4x4 matrices can really be a pain. So let's do an example here. Find the determinant of A, where A is equal to 2, negative 9, 8, 1, 1, 1, 6, negative 1, 6, 0, 5, 7, and negative 4, 8, negative 4, 9. Now, I want to show you guys something, right? What should we do here? We've got a lot of options, but something I noticed right away is that we do have a 0 in the middle, and I do see a 1 above it. Now, what's nice about this column right here? What's nice about this column is that I can use that 1 right here to get rid of this guy and turn them into zeros, right? I know I can do that using the row operation of adding a multiple of a row to another row, right? And we know also that that doesn't change the determinant. So let's write that down. We're going to add 9 times row 2 to row 1, and we're also going to add negative 8 times row 2 to row 4. And so if we do that, we end up with 11, 0, 62, negative 8, 1, 1, 6, negative 1, 6, 0, 5, 7, negative 12, 0, negative 52, 17. Now, isn't this nice? We just have 3 zeros on this column now. So now we're going to do the determinant. And notice that our determinant has not changed because all we've done is use the elementary row operations here. Okay, so let's keep going. I apologize for the outdoor noise, guys. I live in an urban neighborhood, so this is just something we have to deal with, okay? All right, so let's go with the determinant now. And let me remind you of the 4x4, because we do need to look at this sign chart to remind us. So if we're expanding here, I want you to notice that this 1 right here does land exactly on a plus. Very important, or we would have been off by a sign if we forgot to take that into account. Okay, so the determinant, so again, we're going to do, I want to really specify here that this is column 2 expansion, right? We're doing column 2 expansion. So the determinant of A is going to equal, we don't need to write all the other cofactors because they're all going to be 0. So all I really need is the positive 1, it happens to be a 1 there also, times the determinant of, we're going to delete this column and this row, and we're going to write down the matrix that's left, okay? So we're left with we're left with 11, 6, negative 12, 62, 5, negative 52, negative 8, 7, 17. Okay. Now, sadly, there are no zeros here, so this is going to be kind of a pain. So it doesn't really matter which row we choose to expand on at this point. But I'm just going to go ahead and do row 1. When it doesn't matter, I just like to be simple and go with the first row. So remember, this is the chart we need, and I'm only going to do the first row of the chart because that's the only important one. We're going to have to do plus, minus, plus. plus, okay? So this is going to be 11 times, remember, delete that row in that column, we get 5 times 17 plus 52 times 7, right? 5 times 17 plus 52 times 7. Again, I'm doing plus because of the minus 52. Okay, and then we have a minus, remember, because of the sign chart, 62 times 6. Remember, we delete here. I'm on this step now. I'm deleting this guy and this guy. So it's going to be 6 times 17 plus 12 times 7. 6 times 17 plus 12 times 7. And then plus, the last one's a negative 8 though, so plus negative 8 times, after you delete, it's going to be 6 times negative 52 plus 12 times 5. Okay. So if you do crunch all those numbers, you do actually end up with the number negative 4577. Now, even though that seemed like a lot of work, understand that we only had to do one 3x3 determinant here, but can you imagine if we had dealt with this matrix from the beginning without doing the row operation? So if we had dealt with this matrix to begin with, we would have had to do this 3 times instead of just once. So doing that one little row operation step really helped save a lot of time. We were able to fit all the work on this one little slide. Okay. So let's keep going here. I want to give a very important definition. Now, we're going to be looking at this definition right now and doing a little example with it, but this is going to be more important later on in the course. We have something called an eigenvalues. So the eigenvalues of an n by n matrix A are precisely the scalars lambda for which the determinant of A minus lambda times the identity is equal to 0. This is kind of a confusing definition a little bit, so we have to unpack it. This right here is scalar multiplication, right? We're taking lambda, which is a scalar, and multiplying it by the matrix, the identity matrix. So we know that that gives you a matrix, right? N by n matrix. And then we are subtracting n by n minus an n by n, so that's an n by n. And then we're taking the determinant of all of that, and that has to equal 0. Okay. Now, here's another important thing, okay? When you take this determinant, you might get a quadratic, a cubic. It could be a very high degree polynomial that's equal to 0 here. So you could have multiple solutions, and not only can you have multiple solutions, but sometimes they're not real numbers. Sometimes they are imaginary. So let me give this as a note here. Eigenvalues may be real or complex or a combination. In other words, you might have some real eigenvalues and some complex eigenvalues because you're just finding the root of a polynomial. All right, so this is kind of a tricky thing to describe, but I would like for us to do an example. We're going to go over it step by step of finding the eigenvalues of a matrix, okay? So this will be our example. Find the eigenvalues of matrix A, which is -1, 0, 2, 1, 3, 2, 1, 4, 2. Okay. This is a 3 by 3, right? 3 by 3 matrix. And so I want you to remember we are trying to do the determinant of A minus lambda times the identity, right? And in this case, we're going to use the identity of size 3. So let's figure out what this is. Let's start with lambda times the identity of size 3 is going to be, instead of, let me remind you, we don't normally write all this out, but because this is our first time, I want to show you where I'm getting stuff from. It's going to be lambda times this, and that's lambda, 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 0, 0, 0, 0, 0, 0. And so now we're going to do A minus lambda times I3. So that's going to be this matrix minus this matrix. And so, what does it look like? It looks like this. -1 minus lambda. Because we're subtracting 0 in the other spots are not going to change. The only ones that are going to change are those. The rest all stay the same. So that's A minus lambda times I3. And now we need to do the determinant of that matrix. So we can expand on any row or column. So I'm actually going to choose the first column. That's because we have a 0 there, okay? So let's go ahead and do that. The determinant of A minus lambda I3 is going to equal. We have, let me remind you of our sign chart. Remember, our sign chart for a 3 by 3 looks like this. And so we're going this way. So our first one is going to be positive. And so it's going to be -1 minus lambda times, remember, we're doing the determinant of what's left when you delete the first row in the first column. So yes, we do have to multiply 3 minus lambda times 2 minus lambda, and then subtract 4 times 2. Let's write that down first so you guys understand what we're doing here. Sorry, let me delete those two, okay? Just, yeah. So we're doing 3 minus lambda times 2 minus lambda minus 8. And then we have plus 2. Remember, now we're going to delete that column in that row. And so we have 4 minus 3 minus lambda. We have 4 minus 3 minus lambda. Okay. Now, it seems like we have to do a lot of algebra here, and we do, but we have to be careful, okay? The reason I say have to be careful is because we're eventually going to, if we go back to the definition of eigenvalue, we're going to have to set this determinant equal to 0, aren't we? In other words, we're going to want to solve this, and we know eventually we're going to want to have everything factored because that's the only way to solve a polynomial equation like this, okay? So that's why we need to be careful and not multiply things out unless we see that nothing can factor. So here's what I'm going to do. I'm going to do the inside of these parentheses first, and I'm going to see if there's any common factors I can pull out, okay? So let me show you what I mean. Here's what I get. I get, if I FOIL this guy out over here, I end up with 6 minus 3 lambda minus 2 lambda is minus 5 lambda, and then plus lambda squared, and then minus 8. On this one, I end up with 4 minus 3, that's 1 plus lambda. Okay. Now what? Okay. Do you guys notice that this over here, this -1 minus lambda is actually, so you know what, I'm going to write this on the next line. If I pull a -1 out of that, isn't that also 1 plus lambda? So I already notice I have something in common here, but I'm going to simplify the inside, okay? What do we have here? We're going to combine the +6 and the -8. So we end up with, and I'm going to write it in descending order, lambda squared minus 5 lambda minus 2. And then I have plus 2 times 1 plus lambda. Now, this is the cool part. I didn't multiply this guy in because I notice now that the 1 plus lambdas match. Which is nice because now I can factor that guy out and I've got it partially factored now. So if I factor the 1 plus lambda out, what do I have left? I'm also going to factor, by the way, a -1 just because I have a -1 on the first guy. So if I pull a -1 out as well, what's left? I have lambda squared minus 5 lambda minus 2. And because I'm pulling a -1 out of this guy, I'm going to have left a -2 there. Okay. And so that gives me -1 times 1 plus lambda times lambda squared minus 5 lambda minus 4. Let me continue this on the next page because we're running out of space here. So the determinant of a minus 3, no, not 3, lambda I3 is equal to, in factored form, we've got -1 times 1 plus lambda times lambda squared minus 5 lambda minus 4. And by the way, this guy does not factor. This is not factorable, okay? That's important. If it were factorable, we would get some nice solutions to the following equation. But since it's not factorable, we're going to need to use the quadratic formula for that part, okay? So remember the eigenvalues, we have to set it equal to 0. So find the eigenvalues means that we need to solve the following. Take that equation and set it equal to 0. How do you solve an equation like this? Remember, take each factor and set it equal to 0. You don't have to worry about the -1 because it's just a constant. So let's start with 1 plus lambda equals 0, which means that lambda is equal to -1. This is one of our eigenvalues. Now, what about the next one? We've got lambda squared minus 5 lambda minus 4 equals 0. Note that because this doesn't factor, the only way to solve and find these two eigenvalues is to use the quadratic formula. So we get lambda equals, Remember, the quadratic formula would be negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is going to be 5 plus or minus the square root of b squared, so that's 25, minus 4ac, so plus 16 all over 2. This ends up being 5 plus or minus the square root of 41 over 2. And these are our other two eigenvalues. So this means we get 3 eigenvalues altogether. We get negative 1, 5 plus root 41 over 2, and then 5 minus root 41 over 2. Notice that they're all real. That doesn't always happen. Sometimes you do get some imaginary ones, right? But this time they were real. This is very important for the later part of the course. This is our first exposure to finding eigenvalues, but that's not going to be the main focus of this section, okay? You might have a few problems on the homework about this, but we're not going to delve more deeply into this until later, because this is very important for linear algebra and solving differential equations, okay? All right, so we're not quite done here, but we're going to learn a few other cool things regarding the determinant. So let me just see more interesting techniques. So we have another definition here. Let A be an n by n matrix if every element of A is replaced by its cofactor the resulting matrix is called the matrix of cofactors. And is denoted MC, M sub C. Okay, that's the matrix of cofactors. Another definition. The adjoint of the matrix A you denote it this way, ADJA. So that just means adjoint of A is as follows. So the adjoint of A is just the matrix of cofactors transpose. So you find the matrix of cofactors and then you find the transpose of that matrix. This seems like a super arbitrary definition, okay? However, one interesting thing that comes out of this is this gives us another way of finding the inverse of a matrix. Okay, so let's write this down on the next page. So theorem, this is called the adjoint method for finding the inverse of a matrix, it says if the determinant of A is not 0, then the inverse is equal to 1 over the determinant of A times the adjoint of A. Now, this is, in practice, this is not an easy thing to calculate, but I do want to do an example so that you guys can see this in action. And what we're going to do is we're going to use this method to find the inverse of a matrix that we have already done previously. Okay, so this will be a fun example because we'll get to do a problem we've already done and see if we come up with the same answer. So let's look at our example. I want us to find A inverse for A equals 1, 0, 3, 1, 1, 5, 3, 2, negative 1, using the adjoint method. So I want to just put a note here just so you can look back, recall in an earlier 2.6 example, we found A inverse using the Gauss-Jordan method. So we'll be able to compare to see if we get the same answer. Okay? So in order for us to use this formula, we start by finding the determinant of A. Finding the determinant of the matrix. And so I'm going to use, well, let's take a look at it, right? It makes sense that we should use a row or column that has a 0 in it. So how about we use column 1? And just to remind you, there's our sign table for a 3 by 3. And because we chose column 1, we're going to use plus minus plus for this part, okay? Okay, so let's go ahead and do that. Okay, we have 1 times negative 1 minus 10 minus 0 times negative 1 minus 15 plus 3 times 2 minus 3. This is equal to 1 times negative 11 plus 3 times negative 1, which is negative 14. Okay, so we have the determinant of A, right? That's part of the formula that we need. But now we need to find the adjoint of A. So let me remind you of the definition of the adjoint of A. The adjoint of A is the matrix of cofactors transpose. So we're going to start by finding the matrix of cofactors, which means we have to find every single cofactor of the matrix. Okay, let's do that on the next page. And I'm going to write down our matrix here so we have it as a reference. 1, 0, 3, 1, 1, 5, 3, 2, negative 1. So now we find the matrix of cofactors. So let's find all the cofactors one by one. So what would C11 be? C11 is, remember you delete column 1, row 1, and we're left with a determinant we have to find, and we also have to take the sign using the sign table into account, okay? That first guy is positive, So we're left with positive 1 times negative 1 minus 10, which is negative 11, right? What about C12? C12 is this guy. So we're going to delete that row and that column, and we have a determinant that's left. And also don't forget our sign table. That's going to be a negative, right? We have negative 1 times, we have a 1 there, times, and then 0 minus 6, which is positive 6, right? Let's keep going. C13. We're going to delete that row, that column. We're left with 0 minus 3, and that guy is positive. So it's going to be 3 times 0 minus 3, which is negative 9. Oh, sorry. Did I do that right? Oh, I'm sorry. I'm not. Yeah, I made a mistake here. We should not be multiplying by the number. These are just the cofactors. So this should just be positive 1, right? Positive 1. Remember, it's just going to be a positive 1 or a negative 1, right? Positive 1 or a negative 1. So let me be careful here. I misspoke earlier. So yeah, this should be negative 3. Okay, let's do one more here. How about C21? That's this guy right here. We're going to delete that row and that column. And remember, that's a negative in the sign table, so it's going to be negative 1 times, and then negative 1 minus 15, the determinant of what's left, which gives positive 16. We have to do this for every single element in the matrix, okay? So I've already calculated all of these. Let me write them all down. C22 is negative 10. C23 is negative 2. You can calculate these on your own to make sure that you get the same thing as me. C31 is negative 1. C32 is negative 2. C33 is 1. And so we have our matrix of cofactors. Our matrix of cofactors, just put all those numbers that we found into a matrix. Negative 11, 6, negative 3, 16, negative 10, negative 2, and negative 1, negative 2, and 1. Okay, and so we can find the adjoint then, right? The adjoint is going to be the guy that we just got, transpose. So if we do the transpose of that matrix of cofactors, we get the following. Okay, we found the adjoint. This is a lot of work, right? But we're ready finally to find the inverse. So the inverse is going to equal, remember, 1 over the determinant times the adjoint. And we've already found these pieces here. So this is going to be 1 over the determinant. Remember, we got the determinant as negative 14 before. So 1 over the determinant times the adjoint. And so this gives us the following for our inverse matrix. Just multiply that scalar through. And if you look back at our earlier example, I already checked this. This matches our answer from before, which is really nice. It's worth noting that the Gauss-Jordan method is definitely faster. I would not use this method if I were just finding the inverse of a 3x3 matrix. I think the Gauss-Jordan method is still faster, but this leads us to a really nice shortcut for finding the inverse of a 2x2 matrix. So we can use the adjoint method to give us a nice formula, or a nice, I should say, a nice, yeah, I guess formula is correct. It's not really a formula, you know, it's more like to give us a nice shortcut for finding the inverse of a 2x2 matrix. So let's go ahead and do that for a 2x2 matrix. So what is the 2x2 case? The 2x2 case. So let's create a 2x2 matrix here, A, B, C, D. And let's do all the pieces here. It's going to be a lot quicker because there's a lot less stuff. So first, let's do the determinant. The determinant is just going to be A times D minus B times C. Right? And what about the matrix of cofactors? Well, the good news is that when you delete a row and a column, you only have one number left. So you really are just going to have one number. We just have to be careful and keep the plus, minus, minus, pluses into account, right? So what would the first cofactor be? The first cofactor is obtained by deleting the first row and the first column. So we're just left with a D, right? C12. Delete the first row and the first row and the second column. We're left with just a C, but there's a minus sign there. So we need to do a minus C. C21. Delete first column, second row. So C21, yeah. Second row, first column, right? And we're left with a B, and that's going to be negative if we look at our sign chart. So negative B. And then C22, we're left with a positive A. And so our matrix of cofactors is D, negative C, negative B, A. And so we're ready to write down our adjoint. Remember, our adjoint is going to be that guy transpose, which is just D, negative C, negative B, A. And this means that A inverse, remember, A inverse is 1 over the determinant of A times the adjoint of A, which is going to be 1 over AD minus BC times D, negative B, negative C, A. Super nice. This gives us a really clean 2x2 inverse formula that we can use whenever we want. Now, be careful, because if I give you a problem on an exam and I tell you to use the Gauss-Jordan method, you're not allowed to use this method, although you can always use this method to check your work. Okay, so let me write this down. This is the 2x2 adjoint method for finding the inverse. And I would call this a shortcut. The inverse of any 2 by 2 matrix is just going to be 1 over the determinant times the matrix D, A, negative C, negative B. One way you can remember this formula is these two guys get swapped. Notice that AD becomes DA over there. And these two guys turn negative. So again, this is the adjoint method. So let's do a really quick application of this just to show you how easy it is to find the inverse, because for a 2 by 2, this is clearly the fastest way. Okay? So let's find the inverse of 2, negative 5, 6, 1 using the adjoint method. So let's do the determinant first. What's the determinant of A? It's just going to be 2 plus 30, which is 32. So then what's the inverse going to be? It's going to be 1 over the determinant times, remember, swap those two guys and then make the others negative. That's it, right? Or if you want to write it as a single matrix, you can. Just multiply the scalar through. Oops. There you go. We got our answer. All right. I know that we've been going for a long time here. There's just a lot to cover in this section. So we've got one more thing we need to go over, which is Cramer's rule. Okay. Now, before I write down Cramer's rule, well, no, actually, I am ready to write down Cramer's rule. The full explanation of where all this stuff comes from is in the book, but we don't have time to cover it all in class. So we're just going to write down the rule. You've probably seen this before in an intermediate algebra class. Okay, so if the determinant of A is not 0, the unique solution to the n by n system AX equals B is, so x1 is going to equal the determinant of B1 divided by the determinant of A. x2 is going to equal the determinant of B2 divided by the determinant of A. And x3 is going to equal the determinant of, well, sorry, all the way up to xn, which is going to be the determinant of Bn divided by the determinant of A. Now, I do have to tell you what these B's are. So, where Bk is the matrix obtained by replacing the kth column of A with vector B in your system. Remember, B is this guy right here. Okay. So as our very last example, we're going to solve this problem. I do want to say something about Cramer's rule now. This obviously, finding all of these determinants is a lot of work. For a human being, I think that Gaussian elimination is still probably the fastest way to solve an n by n system. So some notes about Cramer's rule. So note 1. If the determinant of A is 0, Cramer's rule cannot be used. That's something we have to remember, okay? Because obviously, if the determinant is 0, you can't divide by 0, right? And so this means that if you have no solution or infinitely many solutions, this method will not work to help give you the solution set. Note 2. I would say Gaussian elimination is probably always still faster for solving a system. However, Cramer's rule is one of the easiest ways to program a computer. To solve an n by n system with a unique solution. Because all you have to do is teach a computer how to do a determinant, and then the computer can solve any n by n system that has a unique solution, or it could tell you that it has no unique solution, although it's not going to be able to tell you what the solution set is if it's got infinitely many. Okay? So let me go ahead and do one example really quick, and we're not going to go through all the crazy computational steps. I'm just going to write down the answers for you, but I do want you guys to at least see how you would set up one example using Cramer's rule. So example, use Cramer's rule to solve the system. Negative 5x1 minus x2 plus 2x3 equals 9. x1 minus 2x2 plus 7. x3 equals negative 2. And 3x1 minus x2 plus x3 equals negative 6. Okay. So we start with A. And we start with needing to know what the determinant of A is. So the determinant of A is going to be, remember we need to take the determinant of this matrix right here. I'm not going to go through all the work of this. I'm just going to go ahead and tell you the answer. It's negative 35. And now we need to do the determinant of all of the BKs. Remember, what's a BK? Starting with B1. This means we're going to take the matrix A, but we're going to replace column 1 with B. Remember, that's B right there. So I'm going to replace the first column in this one with that. And I'm going to write the rest as is, the rest of A as is. So -2, -1, 2, 7, 1. And we end up with 65. Now we're going to do the determinant of B2. This means take matrix A, but replace the second column with B. So it's going to be -5, 1, 3, 9, -2, -6, and 2, 7, 1. If you do that determinant, you get -20. And then finally, the determinant of B3. This means replace the third column with vector B. So we have -5, 1, 3, -1, -2, -1, and 9, -2, -6. So if we do that, we get -5. And so we're ready to write down our solution here. X1 is going to equal, remember we do, by Kramer's rule, it says it's the determinant of B1 divided by the determinant of A, which is going to be 65 over -35, which is -13/7. X2 is going to be the determinant of B2 divided by the determinant of A, which is going to be -20 over -35, which is 4/7. And X3 is going to equal the determinant of B3 divided by the determinant of A, which is -5 over -35, which is 1/7. And there you go. We got our solution. Our solution set is exactly this vector, -13/7, 4/7, 1/7. As I said, this is not, I mean, look, we had to do 4 3x3 determinants here. That is a lot of work. I think Gaussian elimination would have probably been faster. But again, like I said, this is theoretically interesting because it gives you a nice formula for finding the solution to an n/n system. A very nice way to get a computer to do this. But imagine if this were like a 5x5, the computational result here, you would have had to do 6 5x5 determinants, which is insane for a human being to do, but easy for a computer to do. Okay, so just something to keep in mind here. Well, this was a very long video. Thank you for watching, everybody, and hope you have a great day. Take care.